3D manipulator kinematics, or the forward kinematics. Okay, let's connect this with 2D. In 2D, what we did was, the example in 2D is two-link manipulator, which we've studied extensively. So theta1, theta2 are the links. So if you remember, we had set up axis x0, y0, x1, y1, and so on. And then we had written this homogeneous transformation hi with respect to frame I minus 1 as ri I minus 1, oi I minus 1. There were two zeros, and then there was 1. So this is, for example, O1 with respect to 0. Okay, we can write this as OI with respect to I minus 1. This is associated with a rotation matrix, RI, R1, 0, or you can think of this as RI with respect to I minus 1. Right? You just keep doing that, and then you get basically the forward kinematics. Now, this was essentially a 2 cross 2 matrix, 1 cross 2 matrix, 2 cross 1, and 1 cross 1. So the net size of H was 3 cross 3. In 3D, what we'll do is we'll write Ri, the same thing, but as you'll see that I minus 1, 0, 0, 0, and 1. So now this is 3 cross 3, 3 cross 1, 1 cross 1, 1 cross 3. And the size of this matrix is 4 rows, 4 columns. Okay, so this is what we will be using in 3D. Okay, just adding the third dimension. The third dimension comes because the rotation matrix was 3 cross 3, and the position has an x, y, z. So O will be have an x, y, z. Okay, now before we get started with this, we have two types of manipulators. One is of this nature, and then the other one is something like this. So this one is open loop, that is or open loop, or this is a closed loop, right? So there's at least one place where there is a loop joint, this one. So this is a loop joint, and we are not going to be doing closed looped manipulators. They're slightly harder to analyze, but we will not do these manipulators. We'll only look at these manipulators. We've also looked at open loop manipulators pretty much in 2D, right? We've not looked at 3D. Okay, so let's get started with kinematics. Okay, before we start with kinematics, let me draw a schematic. The goal of this exercise is to be able to figure out where is the end effector for given joint angles. So when I do this, when I need to find the position of the end effector, I need to go across the chain using H, right? So for example, if you wanted to compute in 2 dimensions, the position of the end effector, you'll just do H10 times H21, and then this will basically the third row, sorry, the third column, the third, see, 1, 2, yeah. So this row, this column, sorry, the third column of this matrix will give you the position. So we need to basically assemble the H matrices. So there's a similar H matrice in 3D, which I wrote down. So what we can do here is we can concatenate these H matrices, Hi plus 1, I plus 2, I plus 1, so on till Hj, j minus 1. This is only true if I is less than j. So I've shown here I is a link which comes before link j comes, and so on. Okay. If, however, you had I was equal to j, then this will be identity. And then if I was greater than j, this would be H I j inverse. So this is a 4 cross 4 homogeneous matrix. Okay, so what is H? We can write H for different types of rotations and translations. So I'm just going to write a general formula for H for this. There are basically 6 cases. You could have rotation about X, Y, Z, to 3 cases. Translation about X, Y, Z, so 3 more cases. So you could have 6 H's, and I'll write those down. They will actually help us to do the next part, which is forward kinematics for a manipulator. So what is the H? Here is H. H, let's say rotation about the x-axis. So I represent the rotation by an angle phi, 0, 0, 0, cosine phi minus sine phi, 0, sine phi, cosine phi, 0, 0, 0, 0, 0, 0, 1. Okay, so here we have the rotation matrix. This is the rotation matrix associated with rotation about x-axis and by an angle of phi. And there's no translation because that point is just 0, 0, 0. So this is a 4 cross 4 matrix, as you can see, and it is parameterized by the angle phi. You could write something similar for hy. So we'll say that the angle rotation about y-axis is theta. That's the parameter. So then I write that down as my first 3 rows, 3 columns, cosine, sine, 0, 1, 0, minus sine theta, 0, cosine theta. So 0, 0, 0, 0, 0, 0, and 1. Here again, the same thing. The first 3 rows columns give you the rotation about the y-axis. And finally, rotation about the z-axis by an angle psi, cosine psi, sine psi, 0, minus sine psi, cosine psi, 0, 0, 0, 1. So all these 4 cases are revolute revolute joint motion. So if there was a revolute joint, that would be the angle. It will be the homogeneous matrix associated with the revolute joint, but rotation about the different axes. Now, similar to this, we could also write a translation piece, which is associated with only a prismatic joint. So let me write that next. Then we should be ready to do the forward kinematics. So here we look at translation about the x-axis, and I'll parameterize that by ax. So the rotation piece would be simply the identity matrix. So the first three rows, first three columns is I. Now there's ax for the x direction, 0, 0. So it's only translation about the x-axis, and then these are just placeholders. So here we have this piece, which is an identity matrix because there's no rotation, and this piece, which is the translation. And then we can do the same thing for other three. This is prismatic joint motion. Okay, so this is a method to represent the kinematics of a three or of a manipulator. It could also be a 2D manipulator. Okay, so now we've seen the homogeneous transformation. It turns out that to represent the use the DH convention, you actually can concatenate 4 of those homogeneous transformation. First one is rotation about the z-axis by an angle theta I. Translation about the z-axis by di. Translation about the x-axis by ai. And rotation about the x-axis by an angle alpha I. Okay, so what are these? So homogeneous matrices, we have already looked at them. I wrote them down, but let me expand this out. So each of them is a 4x4 matrix. Cosine theta I. You know what? Let me use a shorthand. I have to fit in like 4x4 matrices. So I'll write C theta I, S theta I, where C is sine and S is C is cosine and S is sine. S theta I, C theta I, and 0, 0, 1. So that's one. Second one is this the identity. And then we'll have 0, 0, di, 1. Rotation about the x. So translation about the x. So 1, 0, 0, 0, 1, 0, 0, 0, 1, 0. And then we have 0, ai, 0, 0, 1, 1, 0, 0, c alpha I minus s c alpha I S alpha I, 0, S alpha I, C alpha I, 0, 0, 0, 0, 0, 0, 1. Okay, so C theta I is cosine theta I, S theta I is sine theta I, C alpha I is cosine alpha I, S alpha I is sine alpha I. Okay, and so this particular four H homogeneous matrices can be multiplied together, obviously, and that expansion is actually in the handout. I don't want to spend time writing it down, but typically we will never really, just in Python, we'll just write a function which will do this calculation for us. Okay, now here's the thing. We have to represent 3D motion, right? And a 3D motion consists of six things, six numbers, three for position, three for translation, three positions, X, Y, Z, three translations. It's called a theta X, theta Y, theta Z, right? So if there's an object in 3D, it has six numbers, three for positions where it is in the space, and three for the orientation. Okay, so the expectation is that you would need six numbers to represent an object. It turns out that Denavit Hartenberg doesn't have six numbers in it. It only has four numbers. Those four numbers are these two angles, this distance. Okay, so although there are six, so represent 3D motion, we need six numbers. To represent 3D motion, we need six numbers, but TH convention uses only four numbers, and those are theta I, Ti, Ai, and alpha I. So the question is, what's happening there? It doesn't look right, look correct, right? How can you represent six, have 6 degrees or represent six numbers in space with only four numbers? And so it turns out that it is possible because there's a special way in which DH convention operates. So DH uses this is possible because DH uses a special way to define the axis of the links. So it gets away with just four numbers. And that is why the method is popular, because you don't really need six numbers. You can do only with four. Okay, so that's why I believe it's popular. But there are issues with the method which we will not really tackle. So what are these two? What are these two? What are these special ways? There are actually two things which DH does. One of them, this is actually not in your handout. It basically, well, not this. Sorry. There's two things it does, and I'll write them down. These two special things are okay. So remember, it is basically defining axis of how axis I minus 1 is linked to axis I, and then I is linked to I plus 1, and so on. That is how you build a homogeneous matrix. So what it does is it defines axis of xi is perpendicular to zi minus 1. So this is the axis for the ith link is 90 degrees to the axis, the z-axis of the previous link. The second thing it does is axis of xi is intersects with zi minus 1. Okay, so these two constraints help to get rid of two parameters. Hence, TH uses only 4 parameters. Okay, so this figure is not in your handout, and I'll provide it in the notes. This is basically how AI, alpha I, di, and theta are defined. Okay. It looks very complicated. I have a simple way of doing this assignment. Hopefully that will help you, but you're also free to look at this particular figure and try to figure it out. So let's just skim through this. We'll apply this. I'll have several problems where we'll apply this. That way it'll become clear. There's no other way of understanding this unless you apply. So it's basically, there are 3 steps in the DH. First is we assign coordinate frames. Okay, those axes which we just randomly draw. There's a special way to do it, and that's actually the most tedious step. This is the most tedious step. Once you do the assignment of coordinate axis, you go to the next step. You generate the DH table. Okay, so it basically is a table which goes link by link, and then you have parameters AI, alpha I, di, theta I. So you'll make this table. That's the second step. It's probably the second hardest step. And the easiest one is the actual formula, which is basically taking that table and just plugging into HI and then just concatenating them, just multiplying them so that you get HN with respect to 0. Remember, this is the nth link. So if you have a manipulator with links, this is the nth, this is the 0th. So this is basically telling you what is the position of the nth link, or the not only the position but also the orientation of the nth link with respect to O. That is captured here and here. So Rn0 gives you the orientation of nth axis with respect to O, and then Dn0 is position of nth axis with respect to O. Okay. So that's what we're trying to do, right? We're trying to figure out where this is located with respect to, and that's what you'll get. So that's the end goal. But for that, we need to go through 1, 2, and 3. So let's take a break, and then we'll get to the DH table and how to use it.